The goals of this chapter involving electrochemistry are: determine how to balance an oxidation-reduction reaction in an acidic medium, know how to read the standard reduction potential table, also known as the activity series, utilizing something called the diagonal rule. You can bring that table to the exam. Know how to compute the E cell, voltage of a cell for a reduction reaction, also how to compute it for an oxidation-reduction reaction, not just for a reduction, and not just for oxidation, for both an oxidation and a reduction reaction. And then also know the relationship between E of cell at the standard state, free energy at the standard state, and the equilibrium constant K, large K. The main point of this chapter and all the associated equations is this: if you take two chemicals together and join them via what's known as a salt bridge, so they're really not in communication with one another, this beaker versus this beaker, what happens is that you get an exchange of electrons. As you know, electrons conduct. They can pass through a wire and conduct electricity. And also associated with electron conducting a current is the storage of that charge in volts. So basically you can have mixing two chemicals together via this salt bridge. You can generate a battery, a very crude battery, but you can generate a battery via what's known as a redox reaction, an oxidation reaction at one end and a reduction reaction at the other end. The electrons move from anode to cathode. So that's electrochemistry. So electrochemistry is a combination of electricity, the conduction of electrons, and then actual chemistry. These are the chemicals that are conducting. So a full redox reaction has two components. One is called the oxidation reaction. This loses electrons. So anytime you have an oxidation reaction, electrons are lost in the product side. So electrons are going to be in the product side for an oxidation reaction. And then that's coupled with a reduction reaction. Reduction occurs at the cathode. So anytime you're dealing with a reduction reaction, the electrons are actually in the reactant side. So oxidation, the electrons are in the product side. Reduction, electrons are in the reactant side. There's a common mnemonic that's used. It's called Leo-Ger. Leo, lose electrons, oxidation. Here, zinc loses 2 electrons to become zinc plus 2. And then Ger, G-E-R, copper gains 2 electrons in order to become copper solid. Leo-Ger, lose electrons, oxidation, gain electrons, reduction. So when you cancel out the electrons, no free electrons in any of these half reactions, the 2 electrons cancel, and then you're left with this redox reaction, which is nothing more than an oxidation reaction and a reduction reaction. We can get how much voltage this registers by utilizing this formula, cathode minus anode. And this is a cell notation that you should familiarize with yourself towards the end of the chapter. This is how we write the battery in electrochemistry. These are chemicals that are actually conducting to generate a voltage. So zinc is oxidized to zinc plus 2, so that is the anode. We write the anode first. The 2 lines represent a salt bridge, and then copper plus 2 gets reduced to copper. So anode, salt bridge, cathode. Anode, salt bridge, cathode. This will be a very important sheet to bring to the exam for this chapter. This is the standard reduction potential at 25 degrees. So a couple of important points here. First and foremost, this is at standard state. You can tell by that not symbol. The second important point is that all of these are reduction half reactions. So remember, a full redox reaction is an oxidation half reaction and a reduction half reaction. So what you see here are all just reduction half reactions. And how do I know they are reduction half reactions? Because these electrons are on the reactant side. Okay, so the electrons being on the reactant side, these are all gaining electrons. As an example, fluorine F2 gas is gaining 2 electrons to become 2F minus. The associated voltage with that is positive 2.87 volts. So That's the second important point. All of these are reduction half reactions. We need to combine it with the oxidation half reaction. The third important point is, well, these are reduction half reactions. What do I need to do to get the oxidation half reaction? In an oxidation half reaction, we lose electrons, so electrons are on the product side. So we just flip this. We flip this, electrons are on the product side, we flip the sign. So as F2 gas gets reduced to F minus and gains 2 electrons, if we want to have this being oxidation, 2F minus is going to lose 2 electrons and become F2. That will be associated with minus 2.87 voltage. Positive voltages are a good thing. That means the reaction is moving forward. In fact, that makes intuitive sense. You cannot have any battery with a negative voltage. If you put batteries in your calculator or any other device, alarm clock or what have you, it does not register a negative voltage because that would be a dead battery. So on the flip side, something that's very positive is a reaction that is going to move forward. Okay, it's favorable to the product side. So all of these that are positive are very favorable. So you would expect copper plus 2 to gain an electron to yield copper plus, and associated with that is 0.15 volts. If it's a negative, that means that it's probably, well, it's not going to go. So these half reactions are dead. All right, so you need to combine it with an oxidation half reaction that's so positive enough to give you a positive voltage and a functional battery. So reverse the half reaction, it becomes oxidation. Flip the sign. The more positive it is more better as an oxidizing agent, meaning an oxidizing agent. This is very confusing to a lot of people. An oxidizing agent itself gets reduced. The oxidizing agent is the agent that causes your oxidation. In turn, it gets reduced. So in this table, fluorine is the best oxidizing agent because it gets reduced the best. Moving all the way down on this table, in this sense, is a very good reducing agent because it causes the reduction of something else, in turn gets oxidized. So a reducing agent is something that gets oxidized and is very good at reducing something else. So you see, by reversing this reaction, you get positive 3.05 volts. Lithium loves to be oxidized, so lithium solid would love to lose that electron to become lithium plus. Giving 3.05 volts, it would love to be oxidized, in turn reduce something else. So it's the strongest reducing agent in this table. Fluorine is the strongest oxidizing agent in this table because it loves to get reduced as a half reaction. Lithium is the strongest reducing agent in this table because it loves to get oxidized in this table. The final important point here is something called the diagonal rule, and we'll go over that more in the notes. But if you want a positive voltage, the diagonal rule tells you what can give you a positive voltage. So if you're going to take fluorine, it causes everything below it to flip and become oxidized. That will yield a positive voltage and a battery that is functional and will yield a reaction, a redox reaction that moves forward to the product side. So that is the diagonal rule. Fluorine will cause all of these other ones below it to flip, and when you calculate cathode minus anode, you'll get a positive voltage. Same thing with hydrogen plus. It will cause everything below it to flip if you want a positive voltage, Before we begin into any of the theory, let's balance some equations. So not a typical balancing of equations that you can think of in Chemistry 1, but we're going to balance oxidation-reduction reactions, which a little bit different. So let's define a redox reaction. A redox reaction is an exchange of electrons. either 1, 2, 3, or 4 electrons, or even more. And furthermore, a redox reaction is a combination of both an oxidation half reaction and a reduction half reaction. You add those two half reactions to get the full redox reaction. So a redox reaction is transferring electrons. So we go by Leo-Ger. The element that loses electrons will be oxidized, and who gets those electrons? The substance that gains those electrons will be reduced. It's very important to realize that you cannot have free electrons floating around anywhere. The electrons have to go someplace. They have to go to a partner. And if the electrons are liberated and don't go anywhere, we just cannot have that. So the electrons have to be accounted for in every sense. So when you do your redox reaction, you have to cancel out the electrons. And you cancel it out from the reactant side, cancels out the electrons on the product side. So this is not quite typical of balancing chemical reactions in general chemistry sense, because the first thing we have to realize is that this is in an acidic medium. You can also balance redox reactions in a basic medium, but first we'll do an acidic medium. And so remember, this is a oxidation reduction reaction, so this is 1 part oxidation and 1 part reduction. So in order to do this, we have to go back to our oxidation number rules. So there are 6 rules that you have to recognize in order to determine the oxidation state. So for here we have iron plus 2. So the oxidation state of iron is just the charge of the iron, and in this case that's plus 2. And here the oxidation state of iron is plus 3. So in this case, iron has gone from plus 2 to plus 3. Okay, so that is what we will denote as a half reaction. The other half reaction is MnO4 minus. This is permanganate ion. You don't have to know it to balance this equation. Permanganate ion is going to the manganese, Mn in permanganate ion is going to Mn plus 2. So we know the oxidation state of Mn here is plus 2, but what is the oxidation state of Mn in MnO4 minus? So again, we have to go back to our oxidation number rules that we learned in Chemistry 1. There are actually 6 rules, and oxygen 99% of the time likes to be minus 2. We've got 4 of them here, and the sum of the oxidation states for Mn plus the 4 oxygens must equal to minus 1, which is the sum of this whole MnO4 molecule. So I figured out how to calculate the oxidation state of Mn in permanganate ion. So we have Mn plus 4 O's all have to equal to minus 1. Oxygen likes to be minus 2, 99% of the time. And so we have 4 of those. So Mn plus 4 times minus 2 is minus 8. All of that has to equal to minus 1. And solving for Mn, we have Mn manganese having an oxidation state of plus 7. So here we're going from plus 7 to plus 2. So let's write our half reactions and figure out which one is oxidation and which one is reduction. We have our first reaction here, Fe plus 2 going to Fe plus 3. Remember, we have to divide and sort of deconvolute this full redox reaction to an oxidation half reaction and a reduction half reaction. So we're going from plus 2 to plus 3. In order to balance this out with electrons, we will need to actually have 1 electron in the product side. So plus 2, and we have plus 3 here. Plus 3 minus 1 is plus 2. So in order for Fe plus 2 to go to Fe plus 3, it has to lose an electron. So we balance this by charge, and it's charge balanced. It's already mass balanced. Notice I have 1 Fe here and 1 Fe here. So the Fe's are balanced, but the charge is not balanced. In a redox reaction, we have to balance it out with free electrons. So we lose 1 electron, lose electron oxidation. This is an oxidation half reaction. All right, so that part is done. It's balanced. Obviously, if this is oxidation, then Mn has to be reduced to Mn plus 2. So plus 7 to plus 2 has to be a reduction. But we have an issue here with the oxygens. How do we balance out the oxygens? Well, the key here is to realize that we are in, if we scroll back up, this is the key to solving this problem. We are in an acidic medium. And in an acidic medium, you have lots of water. Okay, that goes everywhere. There's going to be water everywhere because all of these are aqueous. But in an acidic medium, you also have another thing, and that is protons. So there's going to be a lot of H pluses there, and there's going to be a lot of water there. So that's the key point for solving it in an acidic medium, these oxidation reduction reactions. Now, if this was a basic medium, if the problem asks you for a basic medium, you would balance it with OH minus, because basic means there's a lot of OH minus there. This specific problem is asking for the balancing it in acidic medium, so we will balance the oxygens and anything else with water and hydrogen ions. So we have 4 water molecules here. So the 4 oxygens balance out with the 4 oxygens here. Now I need protons. I got 8 hydrogens here. I'll balance the hydrogens with 8 plus. It's perfectly legal for me to do that because I have a lot of H pluses around, and I'm going to do it on the reactant side. So here I'm going to add an H plus, 8 H plus. So now our H's are balanced, our oxygens are balanced. So this problem came about because of the O4. So we had to balance it with waters, and then we balanced the hydrogens in the water with hydrogen ions because we are in an acidic medium. Now we can balance the charges using free electrons. So let's see here, plus 8 minus 1. So that's plus 7 here. And we have a plus 2 here. So it seems to me that we will need to add 5 electrons on the reactant side. Right, so let's try that. Let's add 5 electrons here, 5 E minuses. So if I add 5 E minuses here, remember we balance the charge using free electrons. That's the key in an oxidation reduction reaction. So minus 5 plus 8 is 3. 3 minus 1 is plus 2. I got a plus 2 here, and this is balanced in terms of charge. And another important point here is that electrons are on the reactant side. So 5 electrons are gained by Mn to give you Mn plus 2. This is a reduction half reaction. And now we just add them up. So we add an oxidation reaction with a reduction half reaction. So the key point here is no free electrons. So we will remove the electrons and cancel them out by multiplying this top half reaction by 5. So let's multiply this top half reaction by 5. So we multiplied the first half reaction by 5. This one will stay the same. Let's cancel out our electrons. Remember, it's absolutely critical that you guys realize no free electrons floating around. They're just not good. So I'm going to cancel out this 5 electrons with this 5 electrons. And I think nothing else cancels. So my final reaction is going to be my balanced oxidation reduction reaction. So this is my final answer and a final balanced oxidation reduction reaction. Okay, very different than what we are given with in our problem. So this was our initial problem that we were told to balance. So as a reminder, lose electrons oxidations. Electrons are on the product side of the equation. So in your half reaction, electrons E minus have to be in the product side. And if you're gaining electrons, the electrons are on the reactant side of your half reaction. So this is what we talked about in the introduction of this chapter. Let's say you take some zinc sulfate and immersed in that zinc sulfate is just solid zinc. What you'll see happening is that that zinc solid will be oxidized to zinc plus 2 and 2 electrons. The 2 electrons travel down the wire and they'll go to the separate beaker. In the separate beaker you will have a copper strip enclosed in copper sulfate solution. The 2 electrons are actually going to go here to your copper plus 2 in the copper sulfate solution, and the copper plus 2 will gain those 2 electrons. Where did they come from? Well, they came from zinc here. And that copper plus 2 will be reduced to copper solid. So this salt bridge is basically where spectator ions traverse. So sulfate ion, nitrate ions, potassium ions. To sort of neutralize the charge, you don't want any charge buildup here, and you don't want any charge buildup here. So to keep the charges sort of at bay, so no positives are accumulating, no negatives are accumulating. That's the function of the salt bridge. But the key important point here is that these two beakers are conducting a battery, a very crude battery, and we can get the voltages from the standard reduction potential table. So coming back to this, zinc solid is going to zinc plus 2. There's a loss of 2 electrons. So the way the 2 electrons comes from is that the zinc going to zinc plus 2. How do you balance out the charge? You balance out the charge with 2 electrons. So the minus 2 plus 2 gives you 0, and there's a 0 charge on the reactant side. So this is mass balanced and charge balanced. We can calculate the voltage associated with that, consulting the standard reduction potential table. So that table has this actually for reduction. Because this is an oxidation, we have to reverse the sign. So instead of minus 0.76, it has to be positive 0.76 volts. The cathode is where copper plus 2 gets converted to copper solid. So copper plus 2 getting converted to copper solid. To balance the charge, you need 2 electrons, 2 E minuses on the reactant side. So plus 2 and a minus 2 will give you 0, and there's a 0 on the product side. So this is a reduction half reaction. Reduction occurs at the cathode. So one way to memorize this is red cat eats an ox. Reduction occurs at the cathode, and oxidation occurs at anode. So red cat, reduction, cathode, and ox, anode, oxidation. So looking this up, here we don't have to flip the sign because it's straight from the reduction table. That is positive, and that is positive 0.34 volts. So here, I'll label this blue. Here in the blue we have the oxidation half reaction. Here in the yellow we have the reduction half reaction. The full redox reaction is oxidation plus reduction. So here we'll cancel out the electrons. The 2 electrons on the product side will cancel out with the 2 electrons on the reactant side, and we get our final reaction balanced. Zinc goes to zinc plus 2, copper plus 2 goes to copper. Everything is balanced, and when we add the redox reaction, we add the corresponding voltages, 0.76 volts plus 0.34 volts, and that is 1.10 volts. So positive voltage means that this favors the product side. Positive voltage means that this favors the product side. So delta G, we would expect this to be an exergonic reaction, the delta G at standard state. And if this were an equilibrium reaction back and forth, it would favor the product side. Decay would be large. So another way that you can write this, something that you should know for testing purposes, is this notation. This is called the Daniell cell notation. First we write the anode, so zinc gets oxidized to zinc plus 2, so that's the anode couple. Then we have our 2 lines, which is the salt bridge. And then we have copper plus 2 being reduced to copper. That is the cathode. So anode, salt bridge, cathode. The anode couple, salt bridge, cathode couple. This, actually, if you're just given this on an exam, let me highlight this in blue. If you're given this on the exam, you should be easily, or at least capable enough to convert it back to this. Okay, so these two in blue are equivalent. So what's in blue here is the balanced redox reaction. And from here, you should be able to go to this notation. From this notation, you should be able to get the balanced redox reaction. The rule is anode, salt bridge, cathode. So there's another way to actually solve this problem, and that is using this formula. E cell at standard state is the cathode at standard state minus the anode. And so this is an alternative. So you can use this one, or you can do what I did and kind of just flip, make one oxidation. You notice here I flipped the sign because it was oxidation, and cathode, I kept the sign because it was a reduction, getting these values from the table. Here, this alternative route, which you do not have to use, but it's the one your textbook uses, is cathode minus anode. So reading the cathode from our table, our standard reduction table, it would be So looking at the cathode, we did not flip it because it was getting reduced here. The cathode is plus 0.34 volts. So the cathode is plus 0.34 volts. The anode, so what was our anode here? The anode was zinc going to zinc plus 2. So let's look that up in our standard reduction potential table. So looking that up is zinc plus 2 electrons goes to zinc solid. That was minus 0.76. So here we do not flip the sign if you're going to do the second alternative calculation. So cathode minus the anode. Cathode was 0.34 that we got from the table minus the anode. And from the anode we got minus 0.76. Minus into a minus is positive. This is 1.10 volts. We got the same answer that I did before. So if you are comfortable with this, go ahead and use it. Me, personally, I like to do this. I like to split the reaction, flip a sign, add them up together. But this is what your textbook uses, cathode minus anode. You should get the same answer. A lot of students do this and get the answer flipped. They get the wrong sign, and there's some confusion. But alternatively, some students do not like the method that I teach them because they don't like doing all of this flipping stuff. So whatever suits you, but whatever method you learn, it's very important you realize that. Method 1 here at 1.10 volts, sort of splitting it into the oxidation and reduction half reaction gives me 1.10 volts. Or using this alternative method, cathode minus anode, also gives me 1.10 volts. Both methods are perfectly valid. So this is the big note that I've made here. Taught you was flipping one of the signs that you know is going to be the oxidation. In this method here, there's no flipping signs. You take the cathode value and you take what you believe to be the anode value and then just do cathode minus anode. All right, at the very beginning of this lecture, we talked about the diagonal rule. So we got a positive sign here. We got a positive 1.10 volts. And that positive 1.10 volts means that this is a legitimate battery. In terms of the diagonal rule, how does this work? So let's see the diagonal rule, how it applies to this reaction here. Okay, remember anode, salt bridge, and then cathode. This copper plus 2 minus goes to copper solid at plus 0.340 volts. And looking below it is going to be zinc. Right here, it's below it. And clearly you can see copper, if you remember the diagonal rule, will flip everything below it to yield a positive voltage when you do one of the methods, cathode minus anode, or my method, where you split it up into oxidation and reduction half reaction. So whatever method you employ, the copper is going to flip everything below it, and the copper is going to force this to flip in order to get a positive voltage. So yeah, so copper, by its positioning above zinc, will cause zinc solid to be oxidized to Zn plus 2. Let me repeat that again. Copper will cause this half reaction to flip, causing zinc solid to be oxidized to zinc plus 2, yielding a positive voltage. If it did not yield a positive voltage, it would be negative. It's not going to be negative, it's going to be positive based on the position in our table here. Copper is above zinc. Copper will cause this half reaction to flip, and you'll get a positive voltage. So that's how the diagonal rule works in terms of whether a oxidation reduction reaction will proceed to products or not. Let's do another example. So let's look at maybe Mn and magnesium. So Mn plus 2 will cause this magnesium to be oxidized to Mg plus 2. That will yield a positive voltage. On the flip side, you can say magnesium will cause Mn plus 2 to be reduced to Mn solid. So this diagonal rule works both ways. Okay, if you're going to go below where Mn plus 2 will cause this to flip, it will cause everything below it to be oxidized. Magnesium will cause everything above it to be reduced. It's kind of the same principle. Going down, everything flips. If you're going to go up, everything stays the same. Positive voltages. First of all, taking a half reaction and multiplying it by 2 will not change. Okay, so this is a super important point. It's not 0.53 volts times 2, it's still 0.53 volts. If you multiply this reaction by 4, if you multiply it by 3, whatever it is, it will still be 0.53 volts. Right? So multiplying a half reaction or any of these reactions that you see in the standard reduction potential table will not multiply the volts by the same amount. It's a state function. So whether you have 2 moles or 3 moles, it doesn't matter. The voltage will be the same. So multiplying this by 2, 3, 4 will keep the reaction value, will keep the reduction potential the same. Same rules as before, rule number 2. This is an oxidation, this is a reduction half reaction. You can see the electrons are on the reactant side. We flip it to have the electrons on the product side and making it oxidation. We flip the sign. So flipping the reaction, making a cathode the anode, making the anode the cathode, making one oxidation, flipping it to be reduction, making reduction, flipping it and turning it into an oxidation, changes the sign. This is a very important rule. Okay, so source of mistakes, people will multiply this half reaction by a number, and they'll multiply the voltage by the same number. That's not how it's going to work here when we're dealing with potentials, when we're dealing with reduction potential or an oxidation potential. All right, so here's our standard reduction potential table one more time. Bring this to the exam, and let's review this one more time. So anything below a substance, okay, causes it to be oxidized and in turn a positive voltage. Remember, positive voltage is what we're looking for if we want to build a battery. Most of the times we want positive voltage. So anything below, if you pick a substance, anything below it will cause it to flip, become oxidized, and will yield a positive voltage, will yield a fully functional battery. Okay? Maybe a crude amount of voltage that's stored, but it will be a positive voltage, a reaction, a redox reaction that goes to the positive side. So here this red X basically tells you that oxygen will not cause cobalt to flip. Okay, so that's a big X. What happens is, in turn, what really happens is that cobalt plus 2 will cause water to flip and get oxidized to oxygen and protons. Okay, but this cobalt will not cause this oxygen to flip. So that's the diagonal rule. So this red is a no-no. Looking at this oxygen causing this lead solid to flip and get oxidized to Bb plus 2, that happens and you will get a positive voltage. Do not forget oxidizing agent and reducing agent. So we said that substances here are very good oxidizing agents because they will cause the oxidation of something. In turn, they get reduced. Scrolling down, these substances here are good reducing agents. Substances here like lithium and potassium are good reducing agents because they cause the reduction of something else, in turn get oxidized. So they love to get oxidized and reduced to something else. So that is the diagonal rule. So what is the standard EMF? EMF stands for electromotive force. It's another word that another word for voltage. So what is the voltage? EMF, electromotive force. Really the same thing. Of a galvanic cell made of a cadmium electrode in 1 molar cadmium nitrate solution and a chromium electrode in a 1 molar chromium nitrate solution at 25 degrees C. Standard tells you it's standard state. Also 25 degrees C also is another clue that you are in the standard state. 1 molar cadmium nitrate, so remember all nitrates are soluble, so this would actually be cadmium plus 2. And chromium nitrate, the chromium is going to be plus 3. So which gets oxidized and which gets reduced spontaneously. So spontaneously means we're looking for a positive voltage. So the first thing we want to recognize is that this is cadmium in the plus 2 state. cadmium +2, all nitrates are soluble. This is chromium in the +3 state. Chromium nitrate, all chromiums are soluble. All nitrates are soluble. So let's look at the standard reduction potential table for cadmium and also the standard reduction potential table for chromium. So here, going back to the previous introductory part of this lecture, cadmium +2 electrons goes to cadmium solid, that's minus 0.4 volts. Chromium +3 electrons goes to chromium solid, that's minus 0.74 volts. Both of these are reductions. For it to be spontaneous, we need this to be positive. So how will we get a positive out of this? The only way we can get a positive if we flip this. That is, make this an oxidation reaction, half reaction. That would be the anode, and keep this as the cathode. So let's write these two half reactions and then figure out how we can get spontaneity, which is a positive voltage. So I copied the two reduction potentials from the table, and spontaneously means one of these, we need to make the anode and cathode such that cathode minus anode will be positive. So what I can do here is actually flip this. If I flip this, make this a oxidation reaction and combine it with this reduction reaction, I'll get a positive voltage. So let's go ahead and flip this reaction. So I flip this bottom reaction. By flipping it, it's now become a oxidation half reaction because it's lost 3 electrons. And by keeping this the same, it's become a reduction half reaction. Gain 2 electrons. Now we need to cancel out the electrons, so I'm going to multiply this top half reaction by 2. And remember, this still remains 0.74 volts even though I multiplied this whole thing out by 2. I'm going to multiply this bottom reaction by 3. The impetus behind this is to cancel out my electrons, free electrons. So multiply the top half reaction by 2, the bottom half reaction by 3. This is a 6 electron transfer reaction, so the 6 electrons here will cancel out with the 6 electrons there, and my net reaction is going to be 2Cr plus 3Cd plus 2 goes to 2Cr plus 3 goes to 3Cd solid. So canceling out the electrons, adding up the voltages, this will be spontaneously with 0.34 volts. We can also put this into our Daniel cell notation, the galvanic cell notation. Anode, salt bridge, cathode. The anode here is Cr going to Cr plus 3. Anode is the site of oxidation. Not necessarily, you don't have to put the stoichiometric coefficients in this more abbreviated form of the galvanic cell notation. They usually come about balancing it from here. So basically, if you know 2 out of any of these 3 green circles, you should be able to get the other one. So just a way to communicate between K, E cell, and deltaG. Remember, it's worth noting if deltaG is negative, E cell will be positive, and K will be large. This F here is the Faraday constant, and that's 96,500 joules over volts. Joules over volts. Also coulombs over moles. 96,000 coulombs over moles. That is a constant called the Faraday constant, and you'll have that on your examination. And N is the number of electrons that are transferred. So going back to the above example, we have a 6 electron transfer reaction. 6 electrons are being transferred. Focusing our attention here. So if we do standard state, R is going to be 8.314, that version of R. Standard state is usually 25 degrees, which is 298 Kelvin. And Faraday constant is 96,500 coulombs per mole. By the way, coulombs is the SI base unit for charge, so it's just a unit of charge. So plugging in these values for R, T, and F, we will get this version of E cell. So again, the relationship between E cell and the equilibrium constant. Another version is the log version. So I'll give you the natural log version on the exam. Though the log version is just as valid. The point here, the relationship between equilibrium constant K, E cell, and deltaG. We should know this by now. If deltaG is an exergonic reaction, products are favored. That means the redox reaction gives you positive voltage. It's a functional battery, no matter how crude it is. An equilibrium constant will be very, very large, favoring the products. Equilibrium constant is products over reactants, each raised to the stoichiometric coefficient. If the deltaG at standard state is 0, the E cell is 0, the K is equal to 1. The equilibrium favors neither reactants nor products. Finally, if deltaG at standard state is positive, we call that an endergonic reaction. The K is less than 1, reactants are favored. E cell is negative, which means we have a battery that really doesn't run, negative voltage. And so that redox reaction stays at the reactant side. It does not go push forward to products. Negative voltage, endergonic reaction. The equilibrium constant, products over reactants, is going to be small. Let's do another example here. So calculate the equilibrium constant for this reaction at 25 degrees. So the first thing we want to do is we will consult our table here, or this triangle here. So if you know 2, you can calculate the other in the green circle. I think the way I'll approach this problem is I'll calculate E cell, and then from E cell I should be able to go ahead and calculate natural log of K. From natural log of K I can get K. So here's the equation I will use. R is a constant, will be given. Temperature will be in Kelvin. F is a constant, 96,500. And then N is the number of electrons transferred. So let's split this redox reaction into the oxidation and reduction half reaction. My first half reaction, I have Fe plus 2 going to Fe solid. And Fe plus 2 goes to Fe solid. To balance out the charge, it's going to be 2 electrons. So Fe plus 2 gains 2 electrons to give you Fe solid. Let's look that up in our reduction potential. This is a reduction half reaction, cathode. And going to our table, highlighted in purple, Fe plus 2 E minus is minus 0.44 volts. Now we'll do the same thing for Ag solid going to Ag plus. So Ag solid going to Ag plus, if I add an electron here, E minus, it should be charge balanced. So let's do that. And let's look this up here, and realizing it's an oxidation reaction, the electrons are on the product side. So Ag plus E minus going to Ag solid is plus 0.80 volts, but we need to flip that according to the problem, because in the problem it's Ag solid going to Ag plus. So it's going to be minus 0.80 volts. So here is our oxidation reaction. We flip the sign. Here is our reduction reaction. So let's cancel out the electrons. Again, this is reduction. This thing that has lost the 1 electron is oxidation. Okay, we're doing this based on this equation that was given to us in the problem. And let's multiply this bottom one by 2 to cancel out the electrons. So canceling out the electrons after multiplying this bottom reaction by 2, that oxidation half reaction, let's cancel out the electrons. And then we will add these two reactions together to get our final redox reaction. Adding these two reactions together, we get our final reaction. So don't forget, our final reaction is the same as the reaction that we got above, so we just balanced it. By the way, people often ask me, where does the 2 get in? Well, by deconvoluting this into the half reactions, I get my 2 back. So I got my original equation. Endergonic reaction needs an energy input. We will solve for K here, so let's go ahead and do that in our next steps. So plugging in our minus 1.24 volts here in this equation, and it's a 2 electron transfer reaction. So that's something that I'd like for you guys to recognize. 2 electrons are being transferred here. So I multiply that minus 1.24 volts by 2 times 96,500. We divide by 8.314 times 298. That gives us natural log of K. So putting all this in our calculator will equal the natural log of K. So calculating all of this, I'm getting natural log of K equal to minus 96.594. So K is going to be inverse natural log of that, which is E. So taking E out both sides of the equation will give me E to the power of minus 96.54. So putting on my calculator e to the power minus 96.594, I'm getting k to be at the very small number, 1.12 times 10 to the minus 42. That kind of makes sense. K is very, very small. The voltage is negative. All of these things probably coincide with the fact that this is a non-spontaneous reaction, a reaction that's predominantly favoring the reactant side. In this problem, we're asked to calculate delta G at standard state for the following reaction. First step is let's figure out which reaction or which equation we will use. So delta G here. So I think going back up to my triangle, I'm going to do delta G is going to be, they want us to find delta G. So I think what I'll do is find e to the cell. I know F, I can get N. And yeah, this is the equation I will use. Delta G at standard state is minus NF E cell. So here's the equation I will use. Let's calculate E cell here. So Al plus 3 goes to Al would be my first half reaction. To balance this, I'll take 3 electrons on the reactant side. So plus 3 plus a 3E minus will give me a 0 on the reactant side and a 0 on the product side. And our standard reduction table, Al plus 3 electrons going to Al solid is minus 1.66 volts. So let's write that down as our half reaction. In this half reaction of Mg going to Mg plus 2, I'll put 2 electrons on my product side to cancel out the charge and neutralize it. So this will be 2E minus on the product side. Seeing that in the reduction table, standard reduction table, it's minus 2.37 volts. But in this problem, it is an oxidation reaction. I flipped it according to the nature of the problem. So it's going to be positive 2.37 volts. Since this is an oxidation reaction, we flip the sign from the table, positive 2.37 volts. So we have our first thing is let's cancel out the electrons here. In order to do that, I am going to multiply the top reaction by 2, and I'm going to multiply the bottom reaction by 3. So multiplying the top reaction by 2 does not change this voltage. It's still minus 1.66 volts. Multiplying the bottom reaction by 3 does not change this voltage. It's still going to be positive 2.37. All right, so let's cancel out our electrons. The 6 electrons here. It's a 6 electron transfer reaction, so N is going to be 6. So our final reaction is going to be 2Al plus 3 Mg solid goes to 2Al plus 3 Mg plus 2 aqueous. The voltage associated with that will be 2.37 minus 1.66. Positive 0.71 volts means that this is a reaction that favors the formation of Al solid and Mg plus 2 the products. This should be a battery that's good to go. And now the problem asks us to calculate delta G at standard state. So we got all these voltages from our standard state reduction table. So let's go ahead and plug everything in. This is a 6 electron transfer reaction. Note the units. The volts cancel, and we're left with joules over mole because technically 2 moles of electrons are being transferred. So if your answer is in joules over mole or just joules, I think that should be just fine. All of this in our calculator, I get a value of, I'm getting an answer minus 411.09 kilojoules over mole. So exergonic reaction, positive voltages, all of these point towards good signs of this being a reaction that proceeds towards the products. So kind of like what we have been talking about in our previous chapters, in order to get E at the non-standard state, you need to calculate E naught at standard state. So kind of like the same situation for calculating delta G. You need the delta G at standard state. To calculate E, you need to calculate E at standard state. And this is the natural log version. Q is the reaction quotient. Probably you may see this if you take future chemistry classes, but it's out there, the logarithmic form of the Nerst equation. So once again, you want to think of non-standard states, different conditions than our typical 1 molar at 25 degrees C, pressure usually 1 atmosphere. And here's the number of electrons that are transferred in the redox reaction. So let's do an example here. Will this reaction occur spontaneously? Iron and cadmium, we're at non-standard state conditions. Here is the equation that they are given us. Okay, so here the equation has a single pointed arrow. Technically, a lot of these equations, I don't know if you noticed, they're back and forth. So this could be an equilibrium. It can go forward or it can go backwards. And the question we're being asked is, will this occur spontaneously at 25 degrees under these non-standard state calculations? So it's not K, we're going to use Q. And plug in these concentrations. Now, if they equal to K, then you're at equilibrium. If they're not equal to K, which way will the reaction shift in order to get to equilibrium? So here's our Nerst equation. Let's figure out E cell at standard state. So we have cadmium going to cadmium plus 2 as our first half reaction. So cadmium, I'll highlight that cadmium here, going to cadmium plus 2. That's shown here. To balance this with electrons, it's going to be plus 2 electrons. So that's the 2 electrons that are getting lost. Let's find out where this is in our reduction potential table. Cadmium plus 2 electrons goes to cadmium solid. This is minus 0.4 volts, but in our problem we had to flip it. And so it's going to be positive 0.4 volts because we're having an oxidation reaction. So Fe plus 2 in green going to Fe solid. It looks to me like this is 2 electrons on the reactant side to get them to balance out. And let's figure out in our reduction potential table how many voltages are involved in this reduction. So Fe plus 2 electrons goes to Fe solid. That will be minus 0.44 volts. So let's write that down in our table. We have our oxidation half reaction, also known as the anode. We have our reduction half reaction, also known as the cathode. And let's add them up. This is a 2 electron transfer reaction where 2 electrons are being lost here by cadmium, which is being oxidized. And those 2 electrons are being gained by Fe plus 2, which is being reduced to Fe solid. And our resulting voltage will be 0.4 minus 0.44, so it's going to be minus 0.04 volts. So a reaction that is under standard state will be endergonic, won't happen under standard state. Let's figure out what Q is. Concentration of CD plus 2 in the product side is 0.010. Concentration of our products over reactants, the concentration of Fe plus 2 here is going to be 0.60. So Q here is going to be 0.01 divided by 0.0167, and that will be the Q that's going to go into this. N is a 2 electron transfer reaction. E standard state E naught is minus 0.04, which we got from our standard reduction potential table. So calculating E, I'm getting 0.0126 volts. So under standard state conditions, it's not spontaneous. It will not go to products. Under these conditions of 0.01 CD plus 2 and 0.60 Fe plus 2, it is spontaneous. It will go to products. 0.0126 is a pretty small amount. Just want to bring your attention, natural log of 0.0167 is negative. Negative into a negative is a positive. Another problem is, what is the electromotive force of a galvanic cell consisting of Cd plus 2C cadmium half cell and an H plus H2 half cell? If cadmium is this concentration, H plus is 0.16 molar, and pressure of hydrogen is 0.80 atmosphere. So we have a cadmium Cd plus 2 cadmium half cell and a platinum H plus H2 half cell. So let's go ahead and solve for that. So here are 2 half reaction. One of these will have to be flipped. So let's make this a spontaneous reaction, a positive voltage. So we'll flip the bottom one and make this an oxidation reaction in order to make this a positive voltage. You can also make it a negative voltage, but as a reminder, this is oxidation, and as a reminder, this is the anode where oxidation occurs. We've lost 2 electrons here, and we've gained 2 electrons in the top reactions. The 2 electrons here will cancel out with the 2 electrons in the top half reaction, and we'll add these 2 together. So positive 0.04 volts. Now we'll calculate the EMF of this. Now this is at standard state. If you realize the concentrations that were given in this problem, they are non-standard state, so we will have to use the Nerst equation one more time. So let's go ahead and do that. Before we do anything, let's go ahead and calculate Q here. So products over reactants H plus, don't forget that H plus gets squared because we have 2, so that's where the square comes in, law of mass action. So let's plug in our values. H2 gas in our problem is 0.80 atmospheres, so let's put that in. And then finally CD plus 2, the problem tells us its concentration is 0.2. So let's solve for Q here, plug that in. This is a 2 electron transfer. So 2 electron transfer, meaning our N is going to be 2 in this reaction. I'm getting my Q to be 0.16. We'll plug in 0.16 here. N is 2. And we already calculated E naught in the standard state as 0.04 volts. And let's see what we get here. I'm getting 0.275 volts as my final answer. So magnesium solid goes to magnesium sulfate. In this case, magnesium is in the +2 state. Magnesium sulfate is Mg plus 2 and SO4 minus 2. And then we have nickel plus 2 going to nickel solid. So the key here is realizing that magnesium sulfate is ionic, composed of Mg plus 2 and SO4 minus 2 sulfate ion. And nickel sulfate is composed of Ni plus 2 and SO4 minus 2, the sulfate ion. So these are at non-standard state conditions. Anode, salt bridge, cathode. So the anode is going to be Mg going to Mg plus 2. So Mg goes to Mg plus 2 from magnesium sulfate. And to balance this charge, it's going to be a 2 electron transfer. So this will lose 2 electrons in order for magnesium to go to Mg plus 2. Let's look this up in our table and see what the value is. So magnesium plus 2 electrons goes to Mg solid here. In our problem, it's lost 2 electrons, so we're going to flip the sign and make it positive 2.37 volts. All right, nickel plus 2 from nickel sulfate goes to nickel solid, so let's do that half reaction. So this reduction reaction is minus 0.25 volts, so let's go ahead and add this up and add the voltages. Okay, remember the electrons are going to cancel out. And we can call the top portion where electrons are lost the anode or oxidation. And finally, we can call the top portion where 2 electrons are gained as the cathode or reduction. So adding these two up, we're going to get our reaction, which really corresponds to this notation. So one of the things we want to be fully competent in is going from this galvanic cell notation to the fully balanced redox reaction. So the fully balanced redox reaction is going to be this. I'm getting 2.12 volts now. Now that is E cell at standard state. This is non-standard state. So once again, we're going to have to use the Nerst equation to get our concentrations and our voltages at these concentrations. So here is our Nerst equation one more time. We're going to have to calculate Q again. So Q is products over reactants. So let's go ahead and do that. Q is going to be equal to Mg plus 2 divided by Ni plus 2. Concentration of magnesium ion is 0.40. Concentration of nickel here in this notation is 0.60. So it looks like it's going to be 2/3, which is about 0.667. As our Q, so we're going to plug that Q in here. This is a 2 electron transfer reaction. We know E naught is 2.12, and let's solve for E at these conditions, specifically at these concentrations. So doing that, I'm getting something that's really close to 2.12 volts. So not much of a difference between standard state, which is 2.12, and under these concentrations, 2.13 volts. So part A is decreasing magnesium by a factor of 4. So decreasing magnesium by a factor of 4 will make this not 0.40 molar, but 0.10 molar. So let's plug in 0.10 molar here and see what we get. So Mg plus 2.10 molar, about 4 times less by a factor of 4, gives us a Q of 0.1 over 0.6, which is 0.1667. And let's plug that in here into our new Q equation and see what we'll get. So at a magnesium concentration 4 times less than initially, from 0.4 to 0.1. We get a slight increase in our voltage from 2.12 volts to 2.14 volts. So a little bit of an increase by decreasing one of the concentrations of the magnesium in our reaction. Finally, what happens if we decrease nickel by a factor of 3? So if we decrease nickel by a factor of 3, this will be 0.2. We'll keep our magnesium originally, as in the problem, is 0.4. Keep the magnesium the same and decrease our nickel by a factor of 3, which would make it 0.2. Let's go ahead and calculate that here. Increasing nickel by a factor of 3 makes it 0.20 molar, keeping the magnesium the same as originally in the problem. Keeping the nickel is now at 0.2 molar. We have a concentration reaction quotient Q equal to 2. So plugging that into our Nerst equation, we have a natural log of 2 as K times 0.0257 divided by 2 electron transfer reaction. Let's see what we get when we plug this into our calculator. Plugging that in, I'm getting a value of 2.11 volts. So don't forget to put in units here.